तर नमस्कार विद्यार्थ्यांनो. तर ह्या लेक्चरमध्ये आपण सबग्रुप्स आणि त्याचे काही थेरम बघणार आहोत. तर पहिल्यांदा आपण सबग्रुप म्हणजे काय बघूया. मागच्या लेक्चरमध्ये आपण ग्रुपची डेफिनेशन आणि त्याचे काही एक्झाम्पल बघितलेले होते. तर सबग्रुप म्हणजे काय बघूया. तर सबग्रुपची डेफिनेशन काय आहे? अ सबसेट capital H of group G is called subgroup of G if first one, for all A comma B belongs to H, A star or A dot B also belongs to H, that is H is closed under the same binary operation of G. Second one, identity element must belongs to Z. And third one, for all A belongs to capital H, its inverse A inverse also belongs to capital H. Its inverse also belongs to capital H. So this is how definition of subgroup. Examples. That is what this definition says, that any subset H of group G is called subgroup if it is closed under the same binary operation, existence of identity, and existence of inverse. These three conditions, all the three conditions are from the definition of group. Only associativity is not considered here because associativity satisfies by inheritance. So a group is called H is called a subgroup of group G if these three conditions are satisfies. Example, we know that R star, that is non-zero real numbers. R star is what? X belongs to R such that X is not equal to 0, is group with respect to multiplication. Is a group with respect to multiplication. Then capital H is equal to a subset 1 comma minus 1 is subset of R star. These are the non-zero real numbers and subset of R star. Now if I am taking any two elements, if I validate first property, if I am taking any two elements 1 and minus, so 1 into minus 1 is equal to minus 1, which is belongs to H. Identity also element belongs to H. 1 belongs to capital H, that is identity element belongs to H, and 1 into 1 is equal to 1 and minus 1 into minus 1 is again 1. So each and every element is self inverse, so inverse is also exist. This implies that H is subgroup of group G. This is the notation for subgroup. So H is subgroup of group G. Now next example of subgroup is Z is a subset of R. We know that the set of integer is subset of R, is a subgroup of R with respect to usual addition. with respect to usual addition. Very simple proof. By using simply addition and subtraction, you can show that this z is subset of R with respect to usual, because 0 belongs to z, so identity element belongs to z. Addition of any two integers is again, if a comma b belongs to z, then a plus b also belongs to z, and if a belongs to z, then we know that minus a is also belongs to z, and a plus minus a is equal to 0, that is identity element. Hence every element has also inverse in z, so set of integers is a subgroup of z. Next example, h is equal to nz is subset of z, and nz is subgroup of z with respect to usual addition, is subgroup of z with respect to usual addition. Solution: capital H is equal to nz, capital H is equal to nz, and we know that nz is subset of z. Nz is equal to, what are the elements of nz? These are multiplied by x, and where x belongs to z. That is, for example, 2z is equal to what? 0 is there. First z is what? Minus 3. This is minus 2, minus 1, 0, 1, 2, 3, and so on. This is what z. Now 2z is what? 0. 0 into 2 is 0. 2, 4, 6, minus 2, minus 6, sorry, minus 2, minus 4, minus 6, and so on. So 2z is a subset of z. Now consider any two elements a comma b belongs to nz. This implies that a is equal to nx1 and b is equal to nx2, where x1 and x2 are some members of z. Now a plus b is equal to nx1 plus nx2, which is equal to n into x1 plus x2, and which is belongs to n into z, because x1 plus x2 belongs to z, because x1 plus x2 belongs to z. This shows that this shows that nz is closed with respect to addition, closed with respect to addition. Now we know that 0 belongs to z, 0 belongs to z, and n into 0 is again 0, which is belongs to nz also. So it is again, nz is closed with respect to identity also, that is identity element also belongs to z. Similarly, a belongs to nz. This implies that there exists x belongs to z such that a is equal to nx. Now if x belongs to z, implies minus x also belongs to z, so n into minus x is belongs to nz, and n into minus x is equal to minus time n into x is equal to minus a, so minus a belongs to nz, and hence the element a has its inverse minus a with respect to addition. So all the three properties are satisfied, hence nz is a subgroup of z with respect to usual addition, with respect to usual addition. Now we have a very important theorem which gives the necessary and sufficient condition for subgroup, and that theorem is says that a non-empty subset capital H of a group G is subgroup of G if and only if and only if for any A comma B belongs to H, AB inverse belongs to H. If this condition gets satisfied, then we say that capital H is subgroup of group G. Proof. Suppose capital H is subgroup of G. That is, we have to prove that, assume that first H is subgroup of group G, and we have to prove this condition. And again, we are assuming this condition and prove that all the three conditions of the definition satisfies by using this condition, and prove that H is subgroup of group G. Now suppose H is subgroup of group G. This implies H is a group, because the definition of subgroup, H is itself a group. And consider A comma B belongs to H. This implies B belongs to H, implies B inverse also belongs to H, and A dot B inverse belongs to H for all AB belongs to H. Now conversely assume that conversely assume that for all A comma B belongs to H, AB inverse belongs to H. Now to prove that H is subgroup, consider A belongs to H. So suppose this is an equation star. Therefore A into A inverse also belongs to H. A into A inverse also belongs to, but A into A inverse is what? Identity belongs to H. Hence identity element belongs to H. Next, consider E comma A belongs to H, because we had initially given that H A belongs to H. Now we had proved that by using that element A, identity element also belongs to H. Now consider E and A belongs to H. So using star, E into A inverse is equal to what? A inverse belongs to H. This implies that every element has inverse in H. Every element has inverse in H. Every element has inverse in H. Now consider A comma B belongs to H. Now B belongs to H implies that B inverse also belongs to H. So A into B inverse and its inverse is equal to AB belongs to H. So H is closed under H is closed under star implies that for all AB belongs to H, AB inverse also belongs to, sorry, so this implies that H is subgroup. H is subgroup, hence the proof. That is, using this condition, we had proved that H is subgroup of group G. Next theorem is, let capital H be a non-empty, let capital H be a non-empty finite subset of group G. Capital H be a non-empty finite subset of group G. Then it is a subgroup of G if and only if and only if for all a comma b belongs to H, a dot b belongs to H. That is, any finite group is subgroup if and only just only the closure property get hold, if and only just only the closure property get hold. Next theorem, intersection of any two subgroups of a group is also a subgroup. Intersection of two subgroups of a group is also a subgroup. Proof, let capital G be any group and capital H and capital K are subgroups of group G. Capital H and capital K are subgroups of group G. To prove that H intersection K is subgroup of G. To prove that H intersection K is subgroup of group G. Since H and K are subgroups, implies that E belongs to H and E belongs to K also, implies that E belongs to H intersection K. So H intersection K contains the identity element, that is H intersection K is non-empty. H intersection K is non-empty. Now if H intersection K is equal to singleton E, then obviously H intersection K is subgroup. Now if H intersection K is, then which is subgroup of G. Now if H intersection K is not equal to the singleton E, that is, it contains some more elements other than identity. So consider A comma B belongs to H intersection K. This implies that A comma B belongs to H and A comma B belongs to K. This implies AB inverse belongs to H and AB inverse belongs to K, because H is subgroup of G and K is also subgroup of G implies that AB inverse belongs to H intersection K, and this shows that H intersection K is subgroup of group G. Hence, if H and K are any two subgroups of group G, then H intersection K is also subgroup of group G. But this is not true for the union of groups. That is an important remark, is that union of two subgroups of group need not be a subgroup. For example, H is equal to 2Z, K equal to 3Z. Now 2 belongs to 2Z, that is H, 3 belongs to 3Z, that is K, but 2 plus 3 is equal to 5 does not belongs to H union K. So H union K need not be closed, that is here H union K is not closed under addition. So H union K is not a subgroup, hence union of two subgroup need not be a subgroup. Now in the next lecture we will see some standard subgroups for any given group and some related theorems regarding that.